Welcome to Dr. Boxy Teaches Probability Theory and Statistics. In this lesson, we introduce the very important and fundamental notion of conditional probability. So let us get started. In order to introduce the notion of a conditional probability, let us start once again with the simple situation of throwing a six-sided die. So the sample space is a set of numbers 1 to 6, and we consider two events, capital F, which is throwing a 5, and capital G, which is throwing an odd number. We've seen before that the probability of throwing that 5, probability of F, is 1/6. But what if I ask you a slightly different question? What I want to know is the probability of throwing a 5, but not simply what is the probability of throwing a 5, but what is the probability of throwing a 5 given that we know that we threw an odd number. So now you are given the information to the right of the vertical line, so that is known to have happened. What is then the probability of the event to the left of the vertical line? That is known as a conditional probability. So what we want is the probability of F given G, the probability of throwing a 5, given that you know that you threw an odd number. Now, what does that mean? Well, we're looking at the situation in which we know that we threw an odd number, meaning 1, 3, or 5. And we want to know in that case, how likely is it? What is the probability of having thrown a 5? Well, it's one out of those three possible outcomes. In other words, that probability, the conditional probability in this case, is 1 out of 3. The formal definition of such a notion of a conditional probability is the following one. If we take two events A and B, we define the probability of A given B, or the probability of A conditioned on B, as the probability of A and B divided by the probability of B. The logic behind it is the following. In the denominator, we consider all the possible cases in which B has occurred, because those are the only cases that we need to consider in this case. And in the numerator, we look at, out of all those cases in which B has occurred, in what percentage of them has A also occurred. So that is within the pool of situations in which B happens, in what fraction of them does A also happen? That is the logic behind this definition. And notice that it only makes sense to speak about a conditional probability of A given B in those cases where the probability of B itself is non-zero, because when it's 0, you cannot divide by 0, and that would be a meaningless statement. So this is the definition of a conditional probability. When we consider conditional probabilities, there are two possible ways of considering them given some events. So if we take events A and B, we can consider the probability of A given event B, but we could also look at the probability of B given A. And in general, these are completely different numbers, and I want to show you this via an example. So let's say that event A is being or having been president of the US, and B is being an African American. If I look at the probability of A given B, what does that mean? What I'm actually looking at is, given that we are considering an African American, what is the probability that that person is or has been president of the USA? Well, the answer to that is, out of the whole total group of African Americans, which is approximately 40 million people, one of them, namely Barack Obama, has been president of the USA. Now compare this to the alternate, to the changed probability, the probability of B given A. So that is, given that a person has been or is president of the US, what is the probability that that person is African American? Well, the answer to that is, in the denominator, we're looking at all the people who are or have been president of the US, and there have been 46 of them. And how many of those are or have been African American? The answer is 1. So as you see, in general, those two are completely different numbers, and you need to make sure you know which is the condition and which is the one that you actually want the probability of. To make the point that conditional probabilities are complicated even for people who are knowledgeable of them, I want to show you an example of an experiment that was done in the 1980s. So we are considering patients who either have or do not have breast cancer, And those patients are taking a test for breast cancer, and the test can either give you a positive result, meaning that the test claims you do have breast cancer, and a negative result means that the test claims you do not have breast cancer. Now, tests are not always correct, so it's not because the test says that you do have breast cancer that you have 100% guarantee that you do, and vice versa. So those tests are sometimes wrong. Now, given the following situation, let's assume that we consider a population in which 1% of the patients have breast cancer. We are also given the fact that if we administer the test to the group of patients who have breast cancer, the test will actually predict that they have breast cancer. It will claim that they have breast cancer in 80% of the cases, meaning that in 20% of the cases it will predict for patients who do have cancer that they are cancer-free. And at the same time, for patients who do not have breast cancer, the test will still claim they do in 10% of the cases, and it will correctly claim that they do not have it in 90% of the cases. These are all given to us. The question that we are asked is, what is then the probability of, if you know that the test actually was positive, so the test claims you have breast cancer, what is the probability that you actually do have it? Now, this test was put to 100 medical experts, and 95 of them claimed that this probability was approximately 75%. We will see at the end of today's lesson that they were way off, and by this I absolutely do not mean that expertise does not matter. Expertise is very important. All I'm saying is that conditional probability is actually a sometimes counterintuitive notion, and that experts are not infallible. Now, let us try to build up to being able to calculate this here. We go back to the definition of conditional probability. So we have seen that the probability of A given B is defined as the probability of A and B divided by the probability of B. And if we now isolate the probability of A and B, we find that it is equal to the probability of A given B times the probability of B. Now we can do the same thing but with the probability of A given B. So then we find that the probability of B given A is the probability of B and A divided by probability of A. And we've seen in the very first lesson that the probability of B and A and the probability of A and B are the same thing. And therefore we can write the probability of A and B, we can also write it as the probability of B given A times the probability of A. So we found two different expressions for the probability of A and B, which is either the probability of A given B times PB or the probability of B given A times PA. And let's see how this works. Imagine we take an urn with 5 green balls and 4 red ones, and I pick 2 balls out of that urn. R1 is the event of picking a red ball on the first pick, and R2 is the probability of picking a red ball on the second pick. What is then the probability of picking a red ball in both picks? So what does that mean? What is the probability of picking out 2 red balls? Well, it's actually the probability of R1 and R2, because I want a red ball on the first and on the second pick. Now, according to the expression we found above, we know now that the probability of A and B is the probability of one of them, R2, let's say, conditioned on the other one, conditioned on R1, times the probability of R1. And this we can calculate, because the probability of R1 itself, the probability of picking a red ball on the first pick is, well, there are red balls and there are 4 red balls and 9 balls in total, meaning that on the first pick, P of R1 is 4 out of 9. And what is now the probability to pick a red ball on the second pick, given that in the first one we picked a red ball? Well, on the second pick there are only 8 balls left, And because we picked a red ball on the first one, there are only 3 red balls left for the second pick. In other words, this here, 3 8s times 4 9s, is the probability to pick 2 red balls. And this can be simplified and you find that is 1 out of 6. So this is how this formula can be used in a very simple example. In a slightly more general setting, let us look at an urn again, but this time we have 14 balls in it, 5 green ones, 5 yellow ones, and 4 red ones. And I want to know what the probability is of picking a red ball on the second pick. How can we do that? Well, we can visualize that in the following way. On the first pick, we can either choose a green, a red, or a yellow ball. And for each of those possible outcomes of the first pick, we have 3 possible outcomes for the second pick. If we want the probability that we pick a red ball on the second pick, what we actually want to know is the probability of being here, or here, or here. And so the total probability of picking a red ball on the second pick is the sum of the probability of getting to each of those 3 final outcomes for the second pick. Now, for the first one, the top one, it is the probability of picking a red ball on the second pick, given that we picked a green ball on the first pick, times the probability that we actually got there in the first place, so that the first pick was green, plus the probability for the middle one is the probability of a red pick on the second one, given that we picked red on the first, times the probability of red on the first, plus the probability of the bottom of the 3 options, which is probability of picking red on the second, given that we picked yellow on the first, times the probability of picking yellow on the first one. And now we can calculate each of those. So the probability of green on the first is 5 out of 14. And the probability of picking a red one on the second one, given that we picked a green one on the first one, well, we have 13 balls left after the first pick. And out of those, 4 are red. So we have 4 13th times 5 14th, plus, similarly, if we pick what is the probability of picking a red ball on the first one? Well, that's 4 out of 14, times the probability of R2 given R1. Well, there are 13 balls left, but only 3 of them are red, plus the probability of R2 given Y2 times the probability of the probability of R2 given Y1 times the probability of Y1 is the same as the one for R2 given G1 times P of G1. So that is again 4 13th times 5 14th. And if you add these fractions and simplify, you will find that the answer is 2 7th. So that is the probability that we pick a red ball on the second pick. Now, the logic of what we're doing here is we're looking at all the possible paths that lead us to pick a red ball on the second pick. And we want to formalize this, to generalize this, to get an expression that we can use more generally in cases that are not necessarily easy to visualize this way. Now, in order to do this, we need something known as De Morgan's laws. So what do they say? Well, the first of them claims the following. If we take 3 sets A, B, and C, and we consider the intersection of A on the one hand with the union of B and C on the other, that is the same as considering the union of the intersection of A and B on the one hand and the intersection of A and C on the other. How can we see that visually? Well, let's consider 3 sets A, B, and C. And we will look at first the left-hand side. So we want the intersection of A with B union C. Now, what is B union C? B union C is everything that is either in B or in C. So that is all of C and all of B. So that is what it looks like, all of this. Now, which part of this yellow is intersecting with A? Well, it is this part. The part that I colored in blue is A intersected with B union C. So that is the left-hand side of the equality. If we want to look at the right-hand side, we get the following. We want the union of A intersected with B and A intersected with C. So what is in A intersected with B? Well, that is all of this. What is A intersected with C? That is all of this. And the union of those two is exactly equal to what I colored in blue above. So that is a visual proof of this equality. Similarly, there's another De Morgan law which says that the union of A with the intersection of B and C is the same as the intersection of A union B with A union C. And again, we can prove them visually. For the left-hand side, we want A union B intersected with C. So B intersected with C is this part here. And the union of A with that is everything that I colored in red now, plus anything that is in A. So it's all of this. So this is the left-hand side of the second equality. How does it compare to the right-hand side? Well, on the right-hand side, we want the intersection of A union B and A union C. So what is A union B? A union B is anything that is either in A or in B. So it is all of this. What is A union C? A union C is anything here. So it's all of A and all of C. And what is the intersection of those two? Well, the parts that are colored in green and in yellow are all of A and this part here, which is exactly the same set as the one we had above. So these laws are known as De Morgan's laws. Using De Morgan's laws, we can now state and prove the following theorem known as the law of total probability. We consider event A and events B1, B2, B3, etc. all the way to Bn, with n being some positive integer, with the following conditions. First of all, the union of all the BIs has to be the whole sample space omega. The BIs themselves are mutually disjoint, so the intersection of any two BIs, so BI intersected with BJ, is always the empty set. And the probability of each of those BIs is non-zero, is strictly positive. Well, in that case, it turns out that the probability of some event A is the sum for I going from 1 to n of the probability of A given BI times the probability of BI. So let us try first of all to visually understand what it is that we're doing here. So let's say that this is the whole sample space omega, and what we're doing is we are partitioning that sample space into some sub-parts. So B1 can be this part, for instance, B2 can be this one, B3 will be this one, B4 is here, B5, B6, B7. So in this case, I chose n to be 7. And what I did is I divided omega, I partitioned omega into different parts in such a way that the union of all those parts, the union of B1, B2, B3, all the way to B7 is the whole of sample space omega. And each BI with BJ is disjoint. In other words, they don't have any overlap. Well, in that case, the statement is that the probability of some event A is given by this expression. What is the proof of this statement? Well, we can do it the following way. We can write the probability of event A as the probability of A intersected with omega, because the probability of any A intersected with omega is simply the probability of A. And we can write omega in this case as the union of the B's. So this is PA intersected with the union for I goes from 1 to n of the BIs. And now we use one of De Morgan's laws, which says that the intersection of A with a union of sets is the union of the intersection of A with each of them. So this is the same as the probability of, according to De Morgan, the union for I going from 1 to n of the intersection of A and BI. And now notice that if I take I and j to be different, because BI and BJ are disjoint, it is also true that the intersection of A with BI and the intersection of A with BJ, they're also disjoint because BI and BJ don't have anything in common. And therefore, we can use the third of the defining properties of a probability measure. We saw that the probability of a union of disjoint sets is the sum of the probabilities of each of them. So this is the same as the sum for I going from 1 to n of the probability of A intersected with BI. And now, using the rewritten definition of the conditional probability, this can be written as sum of I from 1 to n of the probability of A conditioned on BI times the probability of BI. And that is exactly what we wanted to prove. So this means it is proven. So this is the statement that we wanted to prove. And notice that that is exactly what we did in the previous example. We looked at picking a ball 2 times out of an urn, and we wanted to know what the probability was of picking a red ball on the second pick, and that is what we call event A, and we partition the sample space into those cases in which the first one was green, the first one was red, or the first one was yellow. So using this formula now, this tells us that that is the same as the probability of R2 conditioned on, I'll write it in the same order as before, G1 times G1. So that is our B1 plus the probability of R2 given R1 times PR1. This is our B2 plus PR3 given Y1 times the probability of Y1. That is our B3. And filling in those numbers just like we did 2 or 3 slides ago, we find that it is 2/7. So that is exactly what we did in the previous slide, but now we see that there is a more general expression, a more general theorem behind it. We now come to one of the most fundamental and important theorems in introductory probability theory, known as Bayes' theorem. And it says the following: just like in the law of total probability, we are taking events A, B1, B2 all the way to Bn with the same conditions as before. The union of all the BIs is the whole sample space omega. They are mutually disjoint, and the probability of each of the BIs is strictly positive, is non-zero. But in this case, we take one additional condition, namely that the probability of A itself is also non-zero, is also strictly positive. Well, in that case, the theorem says that the probability of Bj given A is equal to the expression I wrote on the right-hand side here. Now notice that the reason we need the additional condition here, namely that the probability of A is non-zero, is because on the left-hand side of this equation, we have the probability of something conditioned on A, and that is only defined if the probability of A itself is non-zero. Now, how can we prove this statement? Well, it follows almost directly from the law of total probability. We want to look at the probability of Bj conditioned on A. And that is, according to the definition of conditional probability, equal to the probability of A and Bj divided by the probability of A. Now, in the numerator, we can write this as the probability of A given Bj times the probability of Bj. And that is already equal to the numerator in the expression we want to prove. And the denominator, we have P of A, But we can now apply the law of total probability to it because all the conditions of the law of total probability here at the top are valid in this case. And the law of total probability tells me that P of A is equal to the sum for I going from 1 to n of P of A given Bi times P of Bi. And that is exactly the statement we wanted to prove. This theorem is known as Bayes' theorem. It has far-reaching consequences. It is extremely important and we will use it a lot throughout this course. Let us look at a simple example. So we look at a polygraph test and we represent the test claiming that you are lying. So you take the test, and if the test says you are lying, I will represent that by a plus sign. And if the test claims you are not lying, I will represent that by a negative sign. While you actually telling the truth will be represented by capital T, and you actually lying will be represented by capital L. Now, let's assume that we know some things about the reliability of the test. We, for instance, know that when people are lying, the test will actually claim they are lying 88% of the time, which is not too bad. We also know that when people are telling the truth, that the test will actually claim they are telling the truth 86% of the time. Again, not too bad. But now let's look at a situation where we ask people a question where they don't really have an incentive to lie, so they will tell the truth 99% of the time. Given all of these numbers, what can we say about the following case? What is the probability that you are actually telling the truth when the test claims you are lying? Now, given that based on the reliability studies, the numbers I gave above, you would expect this to be quite low, because if the test is reliable, that means that if it says you are lying, that you probably are actually lying. Well, let's see if that's correct. According to Bayes' theorem, the probability of t given plus is the probability of plus given t times the probability of t. That's the numerator. And in the denominator, we have p of plus given t times p of t plus p of plus given L times p of L. And we fill in the numbers now. Now we know that when you are telling the truth, the probability that the test claims you are telling the truth is 86% of the time, which means that in 14% of the cases, when you are telling the truth, it says that you are lying. So P of plus given T is 14%. And so what we have here is 14 out of 100 multiplied with the probability of telling the truth, which is 99%. And in the denominator, we have 14 out of 100 multiplied with 99 out of 100, plus the probability of plus given L, which is 88%, multiplied with the probability of you lying, given the probability of you telling the truth is 99%, the probability of you lying is 1%. And now plugging in those numbers into your calculator, you will find that this is approximately 94%, which means that when the test claims that you are lying, you still have a 94% probability of telling the truth. In other words, it is totally unreliable. It's simply not true to assume that if the test claims you are lying, that you are actually lying. And these kind of things show you why conditional probabilities are very counterintuitive. At first sight, it may look like the test is reliable, but depending on what it is that you are given and what is known, and depending on the population, the numbers about the population itself, the result may or may not be reliable. And it's very important to be aware of this when interpreting statistics in real life. To make sure you understand the concepts that we have introduced now, I will give you some problem to try to solve on your own. So we are considering two urns. I call them urn A and urn B, and each of them contains some number of green balls and some number of red balls as indicated in the figure. Now the experiment is the following. We start by throwing a coin, which gives us either heads or tails. If it gives us heads, we use urn A and we pick one ball out of urn A. If on the other hand the coin toss gives us tails, then we use urn B and we pick a ball out of urn B. Now the questions that we want to answer is, what is the probability of picking a red ball? That's question 1. And question 2 is, what is the probability of having thrown heads given that we know that the ball we picked was red? Now, the first question, I will leave you to actually calculate this. The result is 31 out of 70, and you can easily find that using the law of total probability. So for the first one, what you will need is the law of total probability. For the second exercise, what you will need is Bayes' theorem, and the result is 21 out of 31. So you can check your calculations to see whether you get the right results. But all you need to do for the first one is the law of total probability, and for the second one, Bayes' theorem. The last concept I want to introduce in today's lesson is that of statistical independence. Now let's start with an example. We take a coin and we throw it up, and we play also with a die. Now event A will be ending up with tails in the coin toss, and event B will be throwing either a 2 or a 5 with the die. What can we then say about the probability of A given B? So what is the probability that the coin toss gives us tails, given that we know that we threw a 2 or a 5 with the die? Well, the answer is, knowing something about what the die did does not tell us anything about what the coin will do. So the probability in this case of A given B is simply the probability of A of throwing tails with the coin, which is 1/2. Similarly, the probability of B given A, so the probability to throw a 2 or a 5, given that we know that we got tails when we tossed the coin, well, it's simply the probability of throwing a 2 or a 5 with the die, because the coin doesn't have any influence on the die. That is P of B, which is 1/3. So knowing something about one of those two results doesn't tell us anything about the probability of the other one. That is what we want to formalize as statistical independence. So we say that two events A and B are statistically independent if the probability of A given B is P of A, and simultaneously the probability of B given A is P of B. So the conditions don't change anything about the probability of the events that we are looking at. I want to show you that events need not be independent. So this is again the definition of statistical independence. Let us look at an urn again, the same urn as before with 14 balls. And I will look at two events. Event A will be R1, meaning we pick a red ball on the first pick, and event B will be picking a green ball on the second pick, so G2. What can we say about the probability of event B, of picking a green ball on the second pick? Well, according to the law of total probability, we can calculate that by looking at all three cases for the first pick, which means we're looking at the probability of G2 given G1 times P of G1 plus etc. for picking a red on the first one plus picking a yellow on the first one. And if we do that and you plug in the numbers, you will see that you find a probability of approximately 36%. Now compare this with the probability of B given A. So now we are given that on the first pick we picked a red ball. What is now the probability of picking a green ball on the second pick? The answer to that is there are 14 balls initially. On the first pick we picked out a red ball, so there are 3 red balls left and 13 balls in general, and so the probability of picking a green ball on the second pick is then 5 out of 13, and 5 out of 13 is approximately 38%. Notice P of B and P of B given A are not equal, and so they are not statistically independent. There are a couple of properties of conditional probabilities that are not difficult to see now. So here is the definition of conditional probability and the definition of independence. And the theorem states two things. The first one is basically saying that notice that for independence we need to check two things. To see whether A and B are independent events, we need to check that PA given B is PA, and also that PB given A is PB. Part A of the theorem tells us that it is sufficient to check one of them, because whenever one of them holds, the other one holds automatically as well. So that is part A of the theorem. Part B of the theorem tells us that being independent is equivalent to the fact that the probability of A and B is the product of the probability of A and the probability of B separately. Let's prove both statements. So for part A, I will prove that part of the equivalence. So we start with the knowledge that P of A given B is PA, and we want to show the other side. So we look at the probability of B given A, and we can write this as the probability, by definition of conditional probability, this is the same as P of A and B divided by PA. And using the definition of conditional probability on the numerator, we can write this as P of A given B times PB. The denominator doesn't change. And now we use what is given to us in this side of the proof, namely that P of A given B is PA. So what we're left with is PA in the numerator times PB, where I used here the given of this side of the proof divided by PA, and this is exactly PB. The PA in numerator and denominator cancels out, and so this proves this side of the equivalence. Now proving the other side is exactly the same. You just exchange the roles of A and B, and you will find that if you start from PB of A given, that P of B given A is PB, you go to the other side simply by doing exactly the same thing, just exchanging the roles of A and B. So this proves part A of the theorem. Part B of the theorem, we want to prove again an equivalence. So first of all, we want to prove that if A and B are independent, then it's true that P of A and B is P of A times P of B. How to do that? Well, we know that P of A and B is always equal to P of A given B times PB. But because of independence, P of A given B is simply PA. And so we have PA times PB. And that proves this side of the equivalence. The other way, what we want to prove this time is independence. So what we need to check is, for instance, this part. So we need to check that P of A given B is equal to P of A. And if that is true, we know from part A of the theorem already that the other side, that the second requirement is also true, and therefore that A and B will be independent. So what we want to check is the first condition. We want to check whether P of A given B is P of A. Well, to do that, what is P of A given B? Well, that is P of A and B divided by P of B. And we are given this time that P of A and B can be written as P of A times P of B. So we have P of A times P of B, and the divided by P of B remains. And now we cancel P of B in numerator and denominator, and we're left with P of A, which is exactly what we wanted to prove. So we proved the first of the two conditions for independence, but from part A we know that that is sufficient because the other one automatically holds as well. And so with this we have proven both statements of the theorem. There is sometimes a misunderstanding about the probability of A or B and the probability of A and B. I've heard students say, for instance, that the probability of A or B is simply the probability of A plus the probability of B. That is in general not true. What is true, as we've seen in one of the previous lessons, is that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And therefore, if the probability of A and B is 0, so for instance, if A and B are disjoint, they don't have anything in common, in that case P of A and B is 0, and in that case we indeed find that The probability of an OR is the sum of them. But that is only true in this special case of disjoint sets A and B. It is not necessarily always true. Similarly, I've heard students say that P of A and B is P of A times P of B. Again, that is in general not true. What is true is that P of A and B is P of A conditioned on B times P of B. And if A and B are independent events, then it is true that P of A given B is simply PA, and therefore that PA and B is PA times PB. So OR doesn't simply translate to plus, and doesn't simply translate to multiplication, but they do in those two special cases here. We can now finally go back to the question we looked at the start of the lesson about expert judgment. So we take a population where 1% of the population has breast cancer, and we're looking at the reliability of the tests. We've seen that given that we know that if a patient has breast cancer, the test will actually claim that she has breast cancer 80% of the time. And if the test claims that if she doesn't have breast cancer in reality, the test will claim that she still has breast cancer in 10% of the time. The question is, how reliable is it when the test claims that the patient has breast cancer? How probable is it that she actually has breast cancer in that case? To answer this question, we now have a tool for it, namely Bayes' theorem. So this is Bayes' theorem, and we will apply it to this. So P of D plus given T plus is this expression here. And now we can fill in the numbers. The probability of T plus given D plus is given, that's 80%. The probability of D plus is 1%. The probability in the numerator, the first term will be the same. And the second term, we need P of T plus given D minus, that is 10%. And the probability of D minus, well, if 1% of the population has breast cancer, that means that 99% of the population does not. And so these are the numbers. And if we calculate it, what we find is a probability of 7.5%. So that says that if the test claims that a patient has breast cancer, she actually has breast cancer in only 7.5% of the cases. Remember that when this question was put to experts, 95 out of 100 of them claimed that this probability was approximately 75%. So they were way, way off. Again, that just means when using conditional probability, be very careful about the mathematics and do not assume that your intuition gives you an immediate correct response. Finally, I want to show you a different way of getting that same result using a table which may make it a bit more tangible. So we have exactly the same situation, the same setting, and the same question, P of D plus given T plus. And we will do it using a table. So the columns represent the people who have cancer and those who don't. And the rows represent those for whom the test claims they do and those for whom the test claims they don't. Now we know that of the whole population, 1% has breast cancer. So just for the sake of argument, let's say that we have a population of 1,000 patients. 1% of them, meaning 10 people, will have breast cancer, and the rest, 990, won't. Now we know that P of T plus given D plus is 80%. So that means of the people who actually have breast cancer, out of those 10, 80% of them will get a positive test. In other words, 8 out of the 10. And the other 2 will get a negative test despite them actually having breast cancer. What do we get in the second column? Well, of those who don't have breast cancer, 10% of them, in other words 99, will still get told that they do have cancer according to the test. The rest of them, being 891, who do not have breast cancer, will actually hear that they don't have breast cancer according to the test. That means that out of 1,000 people, 893 will receive the message that the test claims they don't have breast cancer, and 107 of them will get to hear that they actually do have breast cancer. Now, when I ask what the probability is of D plus given T plus, what I'm actually asking is, of all those people who actually get to hear that the test claims they have breast cancer, so that is 107 people will get to hear that, how many actually do have breast cancer? And those are only 8 of them. And so what we find is this result, and that is the same 7.5% that I showed you on the previous slide. The reason is that because of the fallibility of this test, if the population is such that only a very small percentage actually has cancer, that means that the test becomes very unreliable for those people who test positive. And so again, it's just very important to be aware of these pitfalls when using conditional probability. This was it for today. In the next lesson, we will introduce the notion of random variables and look at the most commonly used distributions. I'll see you then.